Okay. Memory hierarchy and characteristics. There are some characteristics of memory. First, location. Second, capacity. Third, unit of transfer. Fourth, access method. Fifth, performance. Sixth, physical type. Seventh, physical characteristics. And last, organization. Location. There are three main parts of location. The CPU, or we call central processing unit. Internal and external. Capacity is divided into two. Word size. Word size is the natural unit of organization and the number of words or bytes. Unit of transfer. Internal. Usually governed by data bus VID. External. Usually a block which is much larger than a word. Addressable unit. Smallest location which can be uniquely addressed. Word internally cluster on $disk. Access method 1. Sequential. Start at the beginning and read through in order. Access time depends on location of data and previous location, e.g. tape. Direct. Individual blocks have unique addresses. Access is by jumping to vicinity plus sequential search. Access time depends on location and previous location, e.g. disk. Access methods 2. Random. Individual addresses identify locations exactly. Access time is independent of location or previous access, e.g. RAM. Associative. Data is located by a comparison with contents of portion of the store. Access time is independent of location or previous access, e.g. cache. Memory hierarchy. Registers in CPU. Internal or main memory may include one or more levels of cache, RAM. External memory, backing store. As you can see, that is the memory hierarchy diagram. It is like a pyramid. And see it. Yeah, see it to yourself, man. Performance. Access time. Time between presenting the address and getting the valid data. Memory cycle time. Time may be required for the memory to recover before next access. Cycle time is access plus recovery. Transfer rate. Rate at which data can be moved. Physical types. Semiconductor. Example RAM. Magnetic. Example magnetic. Disk and tape. Optical. CD and DVD. Others. Bubble, hologram, etc. Decay. Volatility, erasable. Power consumption is the physical characteristics. Organization. Physical arrangement of bits into words, not always obvious, e.g. interleave. The bottom line, how much? Capacity, how fast? Time is money. How expensive? We don't know. Hierarchy list, register, L1 cache, L2 cache, main memory, disk cache, disk, optical tape. So you want fast? It is possible to build a computer which uses only static RAM. See later. This would be very fast. This would need no cache. How can you cache? This would cost a very large amount. Locality of reference. During the course of the execution of a program, memory references tend to cluster, e.g. loops. Cache. Small amount of fast memory sits between normal main memory and CPU. May be located on CPU chip or module. And this is the diagram for the cache. As you can see, just try to understand it by yourself. Cache main memory structure. Yeah. This also try to understand by yourself. Cache operation overview. CPU requests contents of memory location. Check cache for this data. It presents get from cache. Pass. If not present, read required block from main memory to cache. Then deliver from cache to CPU. Cache includes tags and identify which block of main memory is in each cache block. Cache read operation flowchart. This is the flowchart of cache read operation. Try it to understand by yourself because we're tired. Cache design. Size, mapping function, placement algorithm, read policy, block size, number of cache. Size does matter. Cost. More cache is expensive. You know that. More cost. More cache, more cost. Speed. More cache is faster up to a point. Checking cache for data takes time. Typical cache organization. This is the example of typical catch organization. Comparison of catch sizes. This is the table for comparison of catch sizes. Mapping function. Catch of 64 kilobyte. Catch block of 4 bytes. Catch is 16K to 14 bytes of 4 bytes. 16 M bytes main memory. 24-bit address. And this is the, we call solution or the formula. Direct mapping. Each block of main memory maps to only one catch line. Address is into 2 parts. Please significant with bits identify unique word. Most significant bits is specify one memory block. The MSBS are split into a catch line field R and a tag of S are most significant. Direct mapping structure. This is the structure and this is the, try to understand. Direct mapping catch line table. This is the formulas, Direct mapping organization. This is the diagram of direct mapping catch organization. Direct mapping example. This is the, direct mapping summary. Address length equals S plus W bits. Number of addressable units is equal to S plus word or bytes. Block size. Line size equals 2 words or bytes. Number of blocks in main memory equals 2 seconds plus word per 2 word equals 2 seconds. Number of lines in catch equals M equals 2R. Size of tag equals S minus R bits. Direct mapping pros and cons. Simple, inexpensive, fixed location per given block. If a program accesses 2 blocks that map to the same line repeatedly, catch misses are very high. Associative mapping. A main memory block can load into any lane of catch. Memory addresses is interrupted as tag and word. Tag uniquely identifies block of memory. Every line's tag is examined for a match. Catch searching gets expensive. This is the diagram for fully associative catch organization. Associative mapping example. Associative mapping address structure. Set associative mapping. Catch is divided into a number of sets. Each set contains a number of lines. A given block maps to any line in a given set. Example given. Block B can be in any line of set I. Example given 2 lines per set. Two-way associative mapping. A given block can be in one of 2 lines in only one set. Set associative mapping example. 13-bit set number. Block number in main memory is modulo 2 to the 13th power. As you can see, this is the, the map to time same set. Thank you. That's all. Thank you.